So this is the first set of problems 60 to 62 from our Regents projectile motion practice problems. So we have a football is thrown at an angle of 30 degrees above the horizontal. The magnitude of the horizontal component of the ball's initial velocity is 30 meters per second. All that wording, this basically means that our velocity, horizontal velocity, is going to be 13 meters per second. We know that's constant throughout, so we only ever have to use that 13 meters per second. Then we have the magnitude of the vertical component of the ball's initial velocity is 7.5. So we know that this is going to be our VIY. Okay? And select friction or air resistance. So on the actual Regents, or in the actual Regents, we get the Regents at the end of the year, you'll be given a test booklet that has all these questions in it, and then you'll be given an answer booklet where you write them. So it's saying on the axes in your answer booklet, draw a graph representing the relationship between the horizontal displacement of the football and the time the football is in the air. So this is what it looks like in the answer booklet. So you can tell just from that they only want a sketch. So we know that any displaced d versus t graph is going to be, the slope is going to be our velocity. We have the horizontal displacement. So we know that so consequently we know that the slope is the horizontal velocity, which we know is constant. So in order to be constant, we have to draw a linear line. So basically, if you draw any relatively linear line, the Regents will give you full credit on that problem. So that's worth 1 point. If you do it that way, you get full credit. So 61 and 62. And you can see this is 61 and 62 because it is worth 2 points. The football is caught at the same height from which it is thrown. So we have a total vertical displacement of 0. Calculate the total time the football is in the air. So all work including the equation and substitution with U-books. So this is my workspace and my answer booklet. I'm going to draw my diagram. I know my horizontal velocity is 13 meters per second, and that my initial vertical velocity is 7.5 meters per second. So you can solve this one of two ways. I'm going to solve this by doubling the time first, and then I'm going to solve it a second way. So we know if we're looking at this just at the vertical component, so I'm just going to look at the vertical component of this. Because the horizontal, all we have is 13 meters per second. We don't know the distance, we don't know the time, so we can't use horizontal for this one. So we're actually only going to be able to use the horizontal. We can write our Vx, but we're not going to really use it, just so we have it, at least for this problem. So we're just looking at vertical. We know we have a starting point, and then we know at the top, okay, we're going to be moving at 0 meters per second, the top of the arc, at least vertically, because that's when it's changing direction. So if we bring this over, just looking at the vertical component, so I'm launching it up with an initial velocity, and it's going to reach a height, so that initial velocity is 7.5 meters per second. At the top, we're moving at 0 meters per second. So I know that is for half the trip, because looking at our diagram, if we're getting to the top, that's only half the trip. We have to account for the second half of the trip. So that's why when we find the time, we can double it. So I'm actually going to move this over so I have a little more room. So we know that our initial velocity, VIY, equals to 7.5 meters per second. We know our VFY is equal to 0 meters per second at the top. We know our acceleration due to gravity is negative 9.81 meters per second squared. Okay? We're trying to find the time. So in the homework problem, we actually found the time and then we doubled it at the end. But we can also do it at the beginning. So we can say that I'm going to denote this time half. So this is half our time, because this is what we're telling for half our time. It's equal to our total time divided by 2. So this is actually what we're looking for. We're saying half our time is equal to time divided by 2. So that means our total time, if we're going to rearrange it, our total time is equal to 2 times our half, our t half. we solve for this, or if we plug in this t over 2, we can actually just put that last step in at the beginning and skip a whole explanation. So if we use our equation, we have VIY, VFY is equal to VIY plus A, I'm going to say t over 2. I'm trying to find the total. We know our total time is this. We're solving for t over 2. So, solving for t over 2, that's minus our VIY, minus VIY, VFY, minus VIY, is equal to A, t over 2. Just bring them together. T goes on bottom. So, in order to get the 2 away, I'm going to multiply by 2. In order to get the A away, I'm going to divide by A. That's my cross down. Times by, divide by A, and then I'll multiply by 2. So I just did those at the same time. Now we just have T on one side. Now we'll sub in our values. We still have that 2. We have the final of 0 meters per second minus our 7.5 meters per second over negative 9.81. Putting that out, you get a total time equal to 1.5 seconds. So we've actually solved it in this case. So this is just doing the same thing we did in notes, except for we're just accounting for this, doubling the time at the beginning. So the second way we can do this is redraw our diagram. And now we know that we're just dealing with a vertical zone. So we're going to start off our VI is 7.5. So right here we have 7.5 meters per second going up. So then we at the top, we know we're moving at 0 meters per second, but then we come back down. So from here to here, we're going 7.5 to 0. This is the same exact trajectory, the same exact motion, just in the opposite direction. So instead of going from 7.5 to 0, we're going from 0 to negative 7.5. And that's the distinction here. It has to be negative 7.5 because we're coming down. We're moving in vertically down. So if we look just at this in our, so I'm going to put it over here this time. So we're going to start out here, we're moving up, start out with 7.5, we're going to 0 meters per second, and then we're going to come back down. We're coming down to the same exact trip, the same distance, and because acceleration due to gravity is constant, we're going to end up with the same speed, just in the opposite direction, and that's denoted by our sign. So we have a negative 7.5 meters per second velocity. So that accounts for our whole trip, because at the beginning we have 7.5, and at the end we have negative 7.5. So we can actually just use those to solve. We don't have to worry about doubling anything. VIY equals 7.5 meters per second. VFY equals negative 7.5 meters per second. We know that our acceleration due to gravity is 9.81 meters per second squared. And we're looking at the time. We're going to actually use that same equation. We don't have to worry about that. We have VFY VIY plus AT. Now I solved for it all the way through last time. I'm not going to. If you need to know how to solve for t, just look back. It's the same except for we don't have t over 2. It's the same process. So we're going to subtract the VI minus y and then divide by the a. We're going to get t equals VFY minus VIY over a. We have t for VFY minus that 7.5, or negative 7.5, I should say. And we're going to subtract our 7.5. What you see here is we'll have two negative numbers, so we'll add up to 15 over our negative acceleration. when we get our answer, it's going to be negative 15 over negative 9.81. We're getting the time of 1.5 seconds. That's the second way to solve it. A second way to think about it. And that's that problem. Either one of those ways, you get full credit.